I am Konstantin Pils. I'm a researcher at RAND, and I do research on compute governance with a focus on export controls and the global distribution of AI infrastructure. And when I say AI infrastructure, I mean data centers and the supercomputers inside them. And today, related to that topic, I'm going to talk about my paper, Trends in AI Supercomputers, that I published together with James Sanders, Robbie Rahman, and Leonard Heim in April of 2025. First of all, why do we care about compute? This graph here shows how important compute has been for progress in AI. So this is an investigation into algorithmic progress. And broadly, you can think about progress in AI in two domains. Either you can increase the computational resources to train an AI model, or you can improve the architecture and the methods of training the AI model. And this paper is trying to normalize all of that for compute. So it's kind of trying to translate the algorithmic progress into the compute equivalents. And it finds that compute has been responsible for about 7 orders of magnitude of progress. And meanwhile, algorithmic progress has only been responsible for about 4 orders of magnitude of progress. So this shows us that compute is actually currently the main driver of AI progress. And while algorithms are also very important, compute is really what's driving more and more powerful AI models. And let's briefly talk about where compute matters in the AI lifecycle, because I think that a common understanding of compute is that it matters a ton for AI training, but doesn't really matter much beyond that. And I think I'd like to clarify that a little bit. So already before you even start training your model, you will want to do lots of experiments and look at different potential designs for your AI model. And already in that phase, you will need a lot of compute, because the more research you do, the more potential training runs you run, the more different ways you try your training run before you start it, the more research teams you have involved, the more compute you need. And so more compute is definitely very useful for doing all of this algorithmic research and running different experiments. And then, of course, it's the training run in the second phase of this AI lifecycle. And the training run famously is very compute intensive. Now we're talking about hundreds of thousands of GPUs for the training run. And after that, we see various enhancements, which can be fine-tuning or something like building scaffolding, etc. And also in this layer, we see that compute is playing an increasing role. xAI's Grok 4 allegedly used as much compute for RL fine-tuning than it used for training. So like for the pre-training, as it's also sometimes called. So we see that especially with the advancements of reinforcement learning for language models, we definitely also see a lot of compute being used in this enhancement phase. And then finally, deployment. The more compute you have, the more instances of your AI you can deploy. And increasingly, we've also seen inference scaling, which means that you can invest compute to have your model to have your model think longer, so generate more tokens before it gives a final response. And that is also a way in which compute actually enhances your AI model post-training. And the more compute you throw at the model, the better it gets. I mean, there's diminishing returns, of course, but I think that's broadly true. And the more compute you have, the more users you can deploy your model to. So also in deployment, and particularly in deployment, compute is increasingly important. And I want to stress that because we see that the most of the investments that are happening from the big AI companies right now are actually to expand their deployment efforts rather than their training. They're also rapidly expanding their training efforts, but we see particularly expansions of their deployment efforts. So what are AI supercomputers? For this paper, we define them as a system of chips, and they have to be dedicated AI chips. And these AI chips are things like NVIDIA's GPUs, the H100, increasingly now the B200, the Blackwell chip, the one that's just coming out, and also Google's TPUs and Amazon's Trainium and Inferentia. So like all of these kind of chips that you usually use for AI training. And the way we identify an AI chip is have there been any large-scale AI experiments on this chip, or does it support AI relevant performances? And now we're talking about numerical precision, so particularly 16-bit operations and 8-bit operations, and having optimized tensor cores. So these are all features of AI chips in the context of our paper. And so if a system has these AI chips, we also have a second criteria, and this is that it has to have at least 1% of the performance of the most advanced supercomputer at the time. And we do this so we have kind of like a moving threshold over time, because of course AI supercomputers are rapidly getting more performant. So if we had like a static threshold, we would just include more and more system, and potentially also less and less relevant, and potentially at some point we'd even include your laptop. And to avoid that, we have this 1% moving threshold, so we always check if there's a new system coming online, if it has at least 1% of the performance of the current leading system when it came online. And what do these things look like? Above, we can see data center from the outside. So it looks like a warehouse. It has a lot of these cooling infrastructure around, and those really make sure that the data center doesn't overheat, or that the chips can operate at the temperature that they need to operate, and they do actually produce a lot of heat. So we increasingly see that these data centers are equipped with more and more cooling infrastructure. What you'd also see, not in this image, is that usually there's a dedicated substation, because all of the electricity that the data center needs to be stepped down from high voltage to low voltage, which the AI processors can actually deal with. And so these are like some features that you can recognize the data center from the outside, but you usually don't know if the data center has AI chips or something else. In order to know that, you have to look inside. And from the inside, the data center will look like this. So this is the AI supercomputer. We see all of these server racks on the sides, and inside these server racks will be the servers which have AI chips inside them, and also a couple other components. You also need some CPUs and network switches and memory. And let's briefly look at where in the compute supply chain we are when we talk about data centers. So this is a simplification. The supply chain is very, very complex, but I think it's a very useful one. So when you're producing the AI chips, there's roughly 3 steps that you need to do. The first one is designing the AI chip. So NVIDIA employees, researchers will sit down and work years and years on the architecture for the latest NVIDIA chips. So like on a very complex computer program, and they're designing the 3-dimensional structure of the chip that you later print onto the chip. Once they have that design, they will send that to TSMC, who is like the company is fabricating the AI chips. And this is the process of you take a silicon wafer, and then on the silicon wafer you print a pattern and you etch away some features, and this forms the integrated circuits that later do the computations. So NVIDIA doesn't do this themselves, but they send it to TSMC in Taiwan. And then the chip gets produced, and once you have the chip, you also need to integrate it with some other components. Most importantly, there is HBM, high bandwidth memory, and in order to integrate that with the chip so that they can rapidly call on the model weights which are stored in the memory, you need advanced packaging, where you connect the memory and the logic chip on the same package so they can very efficiently communicate. And so that's the third step, the assembly, testing, and packaging. And then you have your AI chip. Usually gets integrated in a server. That step isn't covered here because it's not as complex, not as important. And then once you have the server, it gets shipped to a data center. To build the data center, you of course need land and all the cooling and IT infrastructure. And there's actually very high demand right now for a lot of that. So sometimes you have wait times of more than a year for example, the voltage transformers for data centers. And then once that's done, you will have to operate your data center. And as long as you're doing that, the data center will always need lots of power. And we're talking about hundreds of megawatts of power these days. So like the equivalent of a small city. And you also need water to efficiently cool the chips. And then you need connectivity to the internet. So you want to be connected to an internet node so that you can run your inference or download the data for training, etc. And then finally, this is the data center level, and the next level is the compute usage level. So an AI company, or maybe it's also in-house, will train AI models and then deploy those AI models, and then they get onto the world. So when we're talking about AI supercomputers, we're really in this part of the supply chain. So the chips are produced, and now they are being deployed. So let's talk about what we did in this paper. So it's actually quite tricky to find a lot of AI supercomputers, and traditional databases like the top 500 don't have any great coverage anymore because they are voluntary submissions. So there's no current effort, or there was no effort before this paper to, like, in a structured way, go out and browse the internet for these kind of systems. So what we did was we developed an automated pipeline, and this automated pipeline starts with Google searches. So Google search has an API where you can basically query it with some parameters, and the parameter we chose here is that we do 12-day intervals. So between 2019 and 2025, in 12-day intervals, we always search for a couple of queries, including AI supercomputer, AI data center, GPU cluster, and all of these kinds of things. And then we get tons of results, and we parse all of those websites that pop up, and then we feed all of those websites into ChatGPT. And we ask ChatGPT, do you find information about an AI supercomputer in this website? And if yes, then please look at all of these details and write down the details as much as you can. And then we pass it to Perplexity, and Perplexity is kind of like a chatbot that is very good at Google search, but I guess it's not actually using Google. And the Perplexity then finds additional information, so we prompt Perplexity to find more information on the user, on the owner, on the type of chip, many different features. Our database has almost 100 different columns where we collect information. And then finally, once we have all of that, we have a huge table, we have to deduplicate it, and finally we will have a manual verification step and then add it to the main database. Additionally, we scrape a lot of existing resources. So I talked about the top 500. There's ML Commons, which is a database of benchmarks for GPU clusters. So some people will submit their GPU clusters there, but it's actually a very scarce source, so not a lot from there, unfortunately. And then there's GPUlist.ai, which is for cloud providers to list some of the offerings they have. So we find some information that way. And then we browse the epoch notable model database, because often developers will say in the paper that they publish with the model how many chips they used, and then we also count that as an AI supercomputer. And then finally, because we know that we wouldn't have great Chinese language coverage, we also got 2 Chinese language analysts on board, and they did Chinese queries and looked at Chinese documents and made sure that we also cover the Chinese ecosystem. And then let's have a look what we found based on this database of more than 500 AI supercomputers that we produced at the end of this research. The first one, which shouldn't be all that surprising given the plot I've showed you earlier, is that AI supercomputers are rapidly increasing in performance. And they're doubling in performance every 9 months, in fact. And let's look at this. I think you'll recognize some of this. Here's the GPT-3 cluster. Here's the GPT-4 cluster. And here's xAI's Colossus, which is currently the largest existing known AI supercomputer. There might be others that we don't cover in this database because we rely on publicly available information, but it's probably one of the largest. And xAI's Colossus has about 200,000 H100s. And as we see this rapid increase in performance, there's a couple other things that also increase exponentially with it. The first one is that the number of chips is increasing exponentially. It's not quite increasing as fast, and that's because AI chips are also getting more efficient. So you have both chip efficiency, so better chips, and you have more chips. And those two factors together, they contribute to this growth in performance. And back in 2019, it was quite uncommon for a system to have more than, say, 10,000 or so chips. So we see a couple, but it's not very common. And now we see routinely that AI developers, or like the hyperscalers, are building systems with hundreds of thousands of GPUs. What's also increasing rapidly is the cost of these systems, and we're only modeling the hardware cost in our paper. In addition, you'd also have to add the data center cost. And we see that back in 2019, usually the largest AI supercomputers were less than 100 million. But that rapidly changed, and in 2022, we already see a lot of systems that are like several $100 million, and this is of course a log scale. All of our plots are on like log scale because we have this exponential increase. And then in 2024 we start to see these billion-dollar systems, and xAI's Colossus is actually $7 billion just for the hardware. If you add the data center cost, that's probably about $10 billion in total. So we definitely see a very rapid increase in the cost of these systems. We also see that the power requirements are increasing exponentially. And to give you an understanding of like what the metrics here mean, a typical city, like a small city, will be something like with like 100,000 inhabitants, will be something like 100 megawatts. So this is roughly the threshold of a small city, and now we see a multiple of that for xAI's Colossus, and that trend is going up steeply. So we expect that power will be an increasingly challenging thing for AI supercomputers to secure. So the power is also doubling, just like the cost, roughly every year. Let's chat a little bit about why we see this exponential increase. So I think the reason we see that is that the AI supercomputers that companies build led to better model performance. And this is because of the scaling laws that have been found in AI, where if you increase the computational resources for an AI training run, you can fairly reliably see capability advances in AI models. That's of course not the only way. We also talked about algorithmic progress earlier, but compute is a very important driver. And as companies saw that there is this relationship that if we increase compute, we will see better model performance, they increasingly started to invest more. So we see the model performance increasing, and that also allowed companies to have more applications for their models. So we saw ChatGPT that attracted, I think it was 100 million users in the first month or so. So like very, very rapid uptake of this technology. And that led to other applications like in search, etc. And we see more and more applications coming out now. And then because of that, companies got more investment, investors got more excited about this technology, and that led to larger AI supercomputers. So we have this reinforcing cycle where we see larger systems that lead to better performance, that lead to more economic applications, and that in turn lead to more investment. And then those investments once again lead to larger AI supercomputers. And let's see what happens if we take these trends that we found and extrapolate them for another couple years. Let's look at the performance, and here we translate to H100 equivalents because I think that's a little bit easier to grasp than FLOP, although there's some uncertainty always because you need to think about which precision you use to normalize to H100 equivalents, but don't worry about that at this point. So right now the largest system we are aware of is the xAI's Colossus with 200,000 H100s. And if these trends continue, then next year in June we'll see a system of roughly 500,000 chips. And then 1 year later, this is going to go to 1 million, and by 2030, if these exponential trends continue, we're going to talk about 20 million H100 equivalents. And give you an understanding, that's roughly the total compute being produced in 2025. So like all of the chips in the world combined are probably roughly 20 million H100 equivalents, and that is going to be needed for just a single AI supercomputer. In terms of the number of chips, that will be roughly 2 million chips. So like more than like 10 times as much as we currently see for the largest systems. In terms of power, we're probably going to be talking or like approaching the 10 gigawatt mark. To give you an appreciation of this, a nuclear power plant or like a typical nuclear reactor will produce something like 1 gigawatt of power. So this would be something like 10 nuclear reactors. And then in cost, we'll approach something like $200 billion. And so my personal take on what I think which of these trends can continue and which ones can't, I think probably 2 million chips seem feasible and to 20 million H100 equivalents. I think chip production will probably be able to sustain that. We have seen rapid increases there, and I expect that those can continue. In power, I'm skeptical that you will be able to get this much power in one location. Instead, what I expect will happen is that companies will increasingly use decentralized training runs, where you orchestrate your training run across several locations so that you don't have to have all your chips in one place. And we already saw this with, for example, Google's Gemini training runs. We don't know how many data centers they used, but we know that they used several ones. And then we also saw this with GPT 4.5's training run, allegedly. Sam Altman said that they used data centers in several locations for that. In terms of the investment, I think this is like a very high number, but it's not crazy looking at how much investment there already is. If you look at Project Stargate, that is between 100 billion and 500 billion of investment, and we're just in 2025, so that could also increase in the future. And then if you look at what AWS, Microsoft, Google are spending on AI infrastructure this year, they all said they are approaching something like $100 billion in capex for the AI data center build out. So I think that is probably feasible. And yeah, that is what I all just went over. And let's look at the data that we found so far. And it actually turns out that the reported announcements of future systems are roughly consistent with what we've already seen. So all of these dots with the cross inside are announcements of future AI supercomputers. And so these are, I think a lot of them are OpenAI Stargate projects, but some of them are also from other hyperscalers, and I think this is the UAE one. And so if we just very naively extrapolate this line, it kind of goes through all of these points. And these are just announcements, so we don't know if they actually just happen in this way. But I think it does give us evidence that it seems like companies are intent on continuing the scaling trend, and I personally wouldn't bet against this scaling happening. And then let's briefly talk about the power needs. In January, I actually wrote a paper about this, and we extrapolated just from looking at historical chip production, how many gigawatts of power AI is going to need. And we find something like California's power capacity will be crossed by 2027. So all AI data centers in the world will need as much power as the state of California does. And then in 2030, we'll see 300 gigawatts, on the order of 300 gigawatts. And what does this mean? I think it primarily means that that's an issue for the United States, because it just can't build its energy grid this quickly, and that's a big problem in the United States right now, and is similarly a problem for Europe and many other developed nations that are struggling to rapidly build power. Let's look at the distribution of the data in our dataset. So who owns all of these systems? If we look at the distribution between the public and the private sector, so public sector means companies and private sector means universities or government systems, we see that back in 2019, the vast majority, something like 60% of AI supercomputers were owned by public entities. So most of those were government entities, like the Department of Energy in the United States has a lot of these national labs that have very significant AI supercomputers, but also elsewhere in the world, China, for example, and Europe. But over the last 6 years, we see a very rapid increase in the sector share of the private sector. So we see that companies are investing more and more in AI supercomputers, and that has given them the upper hand in ownership of AI supercomputers. And the reason for that, I think, really is that AI supercomputers just have become economically valuable, and companies didn't really invest in AI supercomputers back in 2019, or not heavily. They invested a little bit, and it was like a useful thing for R&D, but it wasn't something that you needed for large-scale training and deployment. And that changed over the last couple of years. So we saw a rapid increase, and I think actually the number probably closer to 90%, maybe even above that, because we are more likely to pick up on public systems, because they are usually more transparent about, they are more likely to publish an announcement, etc. And private sector systems aren't. So I think we're actually skewed, and the actual share of the private sector is even higher than this. If we look at the global distribution by country, we find that the majority of systems over the course of our study period was always shared between the United States and China. So back in 2019, it was the US leading, and then China gained a lot of leeway until roughly 2022, and then the US rapidly increased its total share again. And the European Union roughly steady at 5 to 10%, and today it's a little less than 5%. And as we speak, my estimate is that the United States has something like 75% of total compute. China has between 10 and 15%, and then the remaining 10% are split between the EU and other countries. And this can change quickly because of the exponential nature of compute. But right now, the US is leading, and due to the export controls on China, China is actually having a pretty hard time catching up on AI compute. So I think that if the US plays its cards well, the US will continue its dominance in AI infrastructure and lead in total compute. And then let's just briefly look at the map, like what other countries are important here. And please pay attention, this is a logarithmic scale. So this color means that it has 10 times as much. So the US has 10 times as much compute as China, and China has 10 times as much compute as France, and France has 10 times as much compute as Russia. So it's like, it looks like they're all pretty much in the same ballpark, but actually there's 4 orders of magnitude in between all of these countries. So roughly what we see here is that there's lots of countries that don't have any AI supercomputers. Then the US is leading, China is second. Some European countries have like some share, Japan as well. And then there's like a couple countries that have a very low amount of total computing power. And if you're curious about all this, we have a map that you can find on the epoch.ai website. If you just Google trends in AI supercomputers, you will find, I think, the blog post, and then you can click to the data, and we have a nice map, an interactive map, and you can download the data and just explore it if you'd like. And yeah, what caused this US dominance in compute? Why is the US leading so far? So I think one reason for that is that the US has always dominated in previous technologies. So this is something like cloud compute, but also search and Google Media and social media. So many different aspects of the tech stack where the US has led for a long time. And then we also just saw a lot of AI research come out of the United States, and especially some US companies like Google, for example, has done a lot of good AI research. And then the US also just leads in AI, and I think that is the main explanation for this. If you are the leader in AI, you're going to capture most of the market and you're going to invest most into it. And that's like, of course, the chicken and egg thing. So the US led in AI and built more infrastructure, but also because the US had more infrastructure, it led in AI. And then finally, export controls are hindering China, and I think that is the reason why China isn't catching up. And I think if there weren't any export controls, China would probably have a substantially higher share than it does have today. So with that, that is my presentation, and I am very open to getting any kind of questions, and also always happy to discuss this paper and our findings. Please, if you'd like, you can explore the data. It's all available online. And if you'd like to email me, you can do so at cons.f.pils@gmail.com, or you can just Google my name and my email address will pop up along with lots of my publications. So thanks a lot for joining me today, and I hope you enjoyed my presentation about trends in AI supercomputers.